Hello everyone, my name is Lin Zixing. This is a joint work with Brad Hackening from Ivy Business School, Francesco Trevi from UC Berkeley, and my supervisor Giuseppe Carlini from University of British Columbia. Today, I am going to talk about our work, improving context modeling in neural topic segmentation. A well-structured document with clear segments is usually quick to skim and easy to understand. It gives the motivation of topic segmentation task to reveal a document semantic structure by splitting the document into topic coherent textual units. Let's see a real example. An article sampled from Wikipedia which introduces a US city. The body of this article is segmented into sections, like history, geography, and demographics. It is quite easy for readers to get the information of what is going on. However, when we don't have the access to the section or segment boundary info, but only the sentence boundaries, we tend to only read the flat text. This is the same article from before. We can find that it becomes not easy anymore to read and fast extract the main ideas at a glance. To reveal the semantic structure from the flat text, a good topic segmenter can help by segmenting a flat document into the topic coherent segments. And the results of topic segmenter can further benefit other key downstream NLP tasks, such as document summarization, question answering, machine reading, and dialogue modeling. First, let's take a quick look at the existing approaches for topic segmentation. Briefly, the previous work can be categorized into unsupervised and neural-based supervised methods. The gist of the early unsupervised methods is to predict the topic segment boundaries based on the lexical cohesion between sentences or paragraphs. They are usually data-free, but have limited performance and generality compared with the later proposed supervised methods. When it comes to the supervised segmenters, neural-based ones are usually favored due to their better and more robust performance. They can generally be separated in two lines of work. The first line is directly predict segment boundaries by formulating topic segmentation and sequence labeling. The second line is first training neural models for other tasks, and then using the pre-trained model's outputs to predict boundaries indirectly. However, one of the biggest problems for neural ones is their limitation in how to model the context information. And furthermore, the line of neural strategy indirectly does the segmentation, may even require the training data with complex metadata. In this work, we focus on the supervised topic segmenters due to their good performance and generality. Also, to avoid the complex preprocessing and error aggregation, which may happen in the metadata collection, we eliminate the indirect segment inference strategy and finally choose to follow the strategy of framing topic segmentation as sequence labeling problem and building models to directly infer the segment boundaries. However, for this line of work, the main problem is context modeling, which is not transparent and interpretable enough. Now, let's talk about the detailed limitation of context modeling for neural topic segmenters. The first limitation is insufficient local context modeling. Taking a previously proposed simple but effective topic segmenter as an example, I'd like to first give the definition of the problem throughout our work. Formulating topic segmentation as a sequence labeling task. Given a document in the form of a sequence of sentences, we try to predict a sequence of labels assigned to the sequence of sentences, where label 1 means the corresponding sentence is the end of the segment, and 0 otherwise. We can see BiASTM is the mainframe of this segmenter. The BiASTM and other sophisticated RNN-based architectures are able to preserve long-distance information, which can help lots of sequence labeling tasks, such as entity extraction and tagging. However, for topic segmentation, important information for boundary prediction is usually from the local context. Bringing extensive long-distance signals may cause unnecessary noise and hurt models' performance. The second limitation of context modeling for topic seg is about sentence pair coherence. Let's go back to the Wikipedia example. We can observe that in a well-structured document, the semantic coherence of a pair of sentences from the same segment should be greater than the coherence of a pair of sentences from different segments. As shown here, sentence 5 and 6 are more coherent together than sentence 4 and 5, which are from different segments. However, in the previous work, this pattern of sentence pair coherence is only learned implicitly by neural network itself, and we believe with the proper way of explicitly modeling the coherence between sentences, neural topic segmenter can be further enhanced. In order to address the two context modeling limitations given before, in our work, we propose two components which can be added on the neural topic segmenters. To guide neural network to intentionally capture more reasonable sentence pair coherence relations, we propose a coherence-related auxiliary task. To make the basic segmenter focus more on the local context and avoid the noise from faraway sentences, we utilize a restricted self-attention. First, let's learn about the basic topic segmenter we use in this work. It is an enhanced hierarchical attention by LSTM network extended from Kosherick 2018 work. We enhance the sentence encoder of this segmenter by infusing an attention mechanism and BERT. The sentence embeddings generated from attention by LSTM and BERT are concatenated as the final sentence embeddings for label prediction. Once we have the sentence embeddings, we pass them through a label prediction network. As we can see, the prediction network for the basic segmenter is pretty simple. In order to regulate our model to reduce the coherence for the sentence pairs across segments and increase the coherence for sentence pairs within a segment, we design an auxiliary task to predict the consecutive sentence pairs coherence by using the sentence hidden states generated from the bi-LSTM network. This auxiliary task objective is computed based on the sentence pair coherence prediction, and it can be jointly optimized with the original objective. However, how should we obtain the ground truth sentence pair coherence for the loss computing of our auxiliary task? To obtain the ground truth for our introduced auxiliary task, we leverage the ground truth of our segmented training set rather than requiring external annotations. By sliding through all the consecutive sentence pairs, we give coherence score 1 if sentences in the pair are from the same segment, and 0 otherwise. Secondly, as mentioned before, we observe that most segment boundaries only rely on the nearby sentences. The long-distance dependency is preserved by LSTM and self-attention while bringing in unnecessary noises. Hence, we leverage a restricted self-attention mechanism on top of the hidden states of the sentences from bi-LSTM. It only attends the information from the local sentences in a window. Let's zoom in to see the details of a restricted self-attention mechanism. Once we have the sentence hidden states from the last bi-LSTM layer, we first compute the similarity between sentence I and its neighboring sentences within a window size. Then we do softmax on them to get the restricted attention weights for sentence I. Afterwards, we compute the weighted sum of all the sentence hidden states within the window as local context embedding for sentence I. After getting the local context embedding for all the sentences, we concatenate them with the original sentence hidden states and input them to another by LSTM layer. The final part of the presentation is about the experimental results to understand the effectiveness of our proposal. To be more comprehensive, we conduct 3 sets of experiments for evaluation. The first is intra-domain experiment. We train and test the models in the same domain or dataset. The second experiment is domain transfer. We train the models on a large dataset which covers a variety of topics and test them on other challenging real-world testing datasets. Furthermore, we also extend a multilingual experimental setting. We train and test our model on 3 datasets within different languages. In this work, we consider English, German, and Chinese to assess our proposed strategy generality within different languages. For the 3 evaluation settings, we use different datasets for model training and testing. For intra-domain, we train and test our model on Khoi, Rus, and English subset of wiki section respectively. For domain transfer, we train models on English wiki section and tested them on 4 real-world benchmarks which are widely used in previous work. For multilingual experiments, we train models on the English and German version of the wiki section, as well as collect a set of Chinese wiki articles from the Wikipedia dump. Our unsupervised baselines contain BiSeg, GraphSeg, and the chosen supervised baselines cover TextSeg, Sector, which is originally from the wiki section paper, as well as the hierarchical transformer, which was proposed lately. We use the standard PK arrow score as our evaluation metric, since it has become the standard for comparing topic segmenters. It measures the probability of mismatches between the ground truth segments and model predictions within a sliding window K. Since PK is a penalty metric, lower score indicates better performance. So for the intra-domain experiment, we can note that our proposed 4 model with auxiliary task and restricted self-attention outperforms all the baselines. And then we zoom in to investigate the impact of each component. We can see that adding auxiliary task or restricted self-attention gives consistent improvement across all 3 sets. Adding both of them together results in the biggest improvement. So for the domain transfer setting, again, we first compare with the supervised and unsupervised baselines. In this case, our proposal outperforms all the baselines again. From the ablation results, we can observe the same pattern as in the intra-domain, that by adding any of the 2 components, model's performance can be enhanced, and combining them together results in the best performance across all 4 test sets. The experiments for multilingual setting is a little bit preliminary compared with the previous 2, since previous work didn't run their models on the language other than English. Here we only compare our proposal with a random baseline. We can see that our model outperforms the random baseline with substantial margin. However, compared with restricted self-attention, introducing auxiliary task doesn't give that much of the improvement. We think it may be due to the different levels of semantic signals covered in the sentence for different languages. As conclusion of our work, we propose a strategy of using a coherence-related auxiliary task and restricted self-attention to improve the context modeling of neurotopic segmenters. The experimental results show that our strategy is effective within domains, across domains, and on different languages. In the future, we plan to explore if our strategy is applicable for more challenging scenarios, like dialogue segmentation. Also, we plan to search for other NLP tasks which could provide more informative context information for topic segmentation.